Please allow me to introduce Professor E. Murphey, University of Michigan-Dearborn, very briefly. Professor E. Murphey is currently a full professor at the Electrical and Computer Engineering Department and the Associate Dean for Graduate Education and Research at the College of Engineering and Computer Science in the University of Michigan-Dearborn. She has authored over 150 publications in refereed journal and conference proceeding in the area of machine learning, pattern recognition, computer vision, and intelligent system with application to intelligent vehicle systems. She has received many research grants and contracts over the last 20 years from U.S. National Science Foundation, U.S. Department of Defense, and many industrial companies, including Ford Motor Company, Hyundai, and Toyota Research Institute. Please welcome with me our distinguished keynote speaker, Professor E. Murphey, to talk about intelligent vehicle and transportation systems.
Thank you very much for Dr. inviting me. And it's indeed an honor to be here to share with you my research results. What I'm going to talk about is the recent research projects we have been doing in the area of intelligent vehicle systems and vehicle transportation system. Yeah. Okay, that's great, thank you. All right, so why we are doing this? Those are important statistics we have to face. The global light vehicle sales reached 86 million in 2014. And today, people are projecting in 2017, the sales will reach 93.5 million, continue to increase. So what's the consequences? We do need the vehicles, a great deal in, I noticed that in amount, most probably popular transportation tools are private vehicles, right? So it really improves people's life, but we also have to face the consequences. Look at 1.2 million people die every year worldwide. Imagine that. 30,000 in United States. If there was a war cause annual fatality like that, can you imagine? The whole world will be uproar. So also, the environmental consequences, carbon emission, and also resource depletion. Mostly vehicles still burn on gasoline, oil. And also traffic congestion. We all face that in all major cities. So how can we solve that? We definitely still need a vehicle, but we just have to develop more advanced vehicle and also clean vehicle. So research in machine learning and big data technology really provide a lot of opportunity, as you will see, to address all those issues. And in United States, US government and automotive engineering, automotive industry are really focusing on two major areas of research in the next decades. One is connected vehicle, which means through wireless communication, vehicle to vehicle can talk to each other. And V2I stands for vehicle to infrastructure. So on major roads, especially intersection, there will be communication devices so they can receive broadcast messages from vehicle. And vehicle to X, which means vehicle to pedestrian, vehicle to bicyclists, vehicle to motorist, because those people all share roads with the vehicles. A lot of casualty happen. A vehicle hit pedestrian, vehicle hit the bicyclist. So those, if we have connection through communication between vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrian, bicyclist, a lot of fatality can be reduced. I will show you examples in a minute. The second area of research is automated vehicles. Probably people, you have heard about a Google car and driverless cars and so forth. All the major auto companies are competing to get a commercial product to the market. Ford Motor Company is predicting they will have fully automated vehicle systems running in 2021, which is only 4 years away. So major funding in the United States is through the Department of Transportation. So based on last few years research, the Department of Transportation is pushing to realize the connected vehicle on the road. And they decided this will be the major communication device to be used in vehicle-to-vehicle communication. There are already products available, and a lot of laboratory vehicle, experimental vehicle already are equipped with DSRC, but currently the price is very high. So in a few years, they will predict the price will come down, will be realistic to put in the commercial vehicles. Also, from the cell phone companies, they are really pushing the LTE technology because people all have cell phone. So it's a very natural communication way if we want to establish a vehicle-to-vehicle or vehicle-to-pedestrian. But it's a standards, telecommunication standards, there are really no product we can use it yet. So that's the a mobile communication area. So now driverless car has been authorized already in United States, several states. They are allowed to be running on the road. Actually, in the state of Michigan, we already built M-City. University of Michigan, we have M-City. So we built the roads to try to imitate the real streets in Ann Arbor area. Also, we are bringing American Mobility Center. Actually, we will section a large part of the freeways and local for testing the driverless car. It's a major issue to test the vehicles as well. So all those are really attracted a lot of research efforts from industry as well as the United States. So that's the current research funds. So if you look at the automated vehicle, there are a lot of opportunity for AI people and for computer vision, for communications, and also control people. It's very, very important for that. So the American Society of Automotive Engineering defined the automated vehicle into 5 levels. So the lowest level is what we have, what we drive mostly. And level 1 is pretty primitive automation. And example is the adaptive cruise control. Then if you go all the way up, level 5, that's what the most automotive companies are working on, fully automated. And in any environment, it can drive safely. And it is very challenging. But for a long time, we will see actually, and level 2, probably level 3 coexist with level 0. That's the most challenging part we are facing in the next few years. Okay, so that kind of research illustrates why we are doing all this. Most challenging scenario in the vehicle industry is the intersection part. A lot of accidents happen, especially in a lot of developing countries. People try to compete for the road to get ahead, and people usually ignore the traffic rules and so forth. That's the most dangerous part. So we want to develop an artificial intelligence system, for example, can warn drivers what are the likely violations of traffic control device. And also we want to broadcast what this driver is doing actually potentially violate the rule, broadcast to the other vehicles. And also, in order to implement such a system, we will need the sensors to be put on the vehicle, and also driver interface with each vehicle. And we need the infrastructure-based technologies. For example, if we have a connected vehicle, this vehicle trying to turn left and had a tendency of turning left, which is wrong, and this vehicle tried to go this way, then if you have the connection, through the wireless communication, and those kind of situation can be avoided. And this is another example. This is a blind spot for this red vehicle, but if we have the communication and this motion of the yellow vehicle can be broadcast to the red one, and such a incident also can happen. But it really requires a lot of research in vision, sensor, control, and communication to make this happen. So the technology will be available, and with the communication devices and also research in intelligent vehicle systems. Now, one very important part of what we are working on is the V2 pedestrian collision avoidance. That casualty actually happen in a lot of countries. If you can see, one example is that a pedestrian is walking and this car really couldn't see because this field of view was blocked by this vehicle, and this pedestrian couldn't see either. So if there's a wireless communication, then the pedestrian will know the vehicle is coming this way, and potential collision can be avoided. And same here in parking lot. A lot of casualty happen is that someone tried to pull out a parking spot, then a pedestrian walking by, and also collision can happen. So those are the major issues we need to address to avoid collision. So in order to implement such a technology, one system should be implemented in the vehicle, try to detect whether there are pedestrians in the way that potentially can cause collision, as well as at the pedestrian side, and most likely eventually we will have a cell phone communication and broadcast the pedestrians' whereabouts, and also for the vehicle has a communication and broadcast whereabouts, then we will be able to give warning to the vehicle and to the pedestrian to avoid such a collision. Okay, so how I'm doing? Is the time, am I okay? Oh boy, I haven't even reached the part I wanted. So this is just further describing the V2P. Okay. So while all this work, why it's so challenging? Because we have to face the big data problem for the intelligent vehicle system. So what do we mean by the data? What are the data available? And for one example is that from the vehicle side, we have hundreds of sensor data at a very high frequency rates. They are recorded, need to be waiting to be used. And also in United States, North America, and European country, they already have digitized all their roads, freeway and local and all those roads. So traffic sensors are already placed on those roads. So those traffic sensors are collecting data 24/7. And can you imagine this kind of huge data set we are waiting to use, they are waiting to be used. And in our research lab, we have been downloading all the roads, geometric roads, information in all Michigan and Ohio, all streets. In addition to that, we also are downloading the traffic data 24/7. So you can see every day we have to store over 460 million bytes of data. And also, we have all real-world driving data. And all auto companies are collecting real-world driving data in order to come up with intelligent system can drive as smarter or smarter than human. And all those, you will see the data size. For connected vehicle in University of Michigan, we have over 3,000 vehicles equipped with V2V communication devices. And we have been collecting data, and 4.4 million trips travel within over 1,500 days. So the data size about over 5 terabytes. All those really reflect the big data complexity, we have the volume, we have the variety, we have the velocity, we have the veracity, and the value. That's why we're working on. Okay, so this just shows the data mining research activity going on in my research lab. We have the raw data, V2V communication data. We also have individual driving data, weather data, and also we have real traffic data provided by GIS company to us, and the road information. So we do the data mining, build our own knowledge base. We are able to support a number of research shown here. Now, I know I'm running out of time, so I only will show you one research projects use the big data I just introduced earlier. So what we are trying to do is to predict traffic speed at the beginning of every trip. So why we're doing this? Because if you have done the energy optimization in vehicle, theoretically we can prove if we are given the driving speed profile, actually we can come up with energy control strategies that will reach the optimal energy consumption or minimal energy consumption. So it is but how do we know what the traffic speed could be? One way is that if I can predict the traffic flow along the road, so a driving speed profile should be very close to that, then I can optimize based on this prediction. So this is just a mathematical notation for any traveling route from an origin to a destination. We can present as a function of XP. XP is any point along the route. That point can be the sensor location or any specific point between the sensor or special locations. So what we want to predict is the traffic speed at the time of T0 at the beginning of the trip. And what will be the likely speed profile from the O to D. So we already are given the sensor data. Traffic sensor at each sensor location will give me every 5 minutes what is the speed will be. But it's only the historical data. At the time when I predict, I only have the speed available in those sensor locations at the time when the trip starts. But as your time goes on, speed will change. That's the dynamic part. And also the traffic sensor distribution distances are all vary. They are not constant. And this is just an example. We have 32 trips. And in the same route, you can see the variation of the speed profile. Okay, so we have two major systems. One is the speed prediction neural network system. It tries to predict along each sensor location what is the likely speed 5 minutes from now, 10 minutes from now, all the way. Predict the future. So it eventually generate a speed and all temporal matrix, as we will show. The second system we call dynamic traversing speed profile. It will connect, because the distance is different. It will give me the speed profile at every sensor location as the vehicle travel along. So altogether, we have 24 neural networks. It's divided between the Monday through Friday traffic and Saturday and Sunday traffic. Within each category, we have congested level of neural networks and also non-congested neural networks. And the prediction time will be vary 5 minutes from now, 10 minutes from now, and all the way to 30 minutes or 1 hour, and so forth. Jay can keep on going. Am I doing okay, the time? Okay. So this gives you example. This is the traveling route. At any position, I will take the sensor data, we call downstream data, plus the upstream data at the time t equal to 0. Then I will predict, as time goes on, the future speed will be in those traveling spot. Okay. So the input to the neural network, it really depends on how long you will predict. This is the time axis. And then also it will take the data in the historical data. At the time t equal to 0, that's when the trip begins. But it also takes the time one step before the t equal to 0, because as we know, the traffic you want to predict in the future very much rely on what's the upcoming traffic as well. So all those are used as input to our neural network as we go on. And so eventually all those neural networks will fill up this temporal time-space traffic map. And the dynamic traverse program will generate from the trip beginning the vehicle traveling speed. And based on when that vehicle will travel to the next station, then it will pick up the appropriate speed. And I just want to show you, last a few minutes, show you the experiments we conducted to evaluate our system. We download the real traffic data collected by the California Freeway performance measuring system. So it's a section of the Interstate 405 north. Probably you know, if you've been to California, it's the busiest and most congested freeway in the United States. And the section we took, about 26 miles long, contains 52 traffic sensors. And the posted speed limit is about 65 miles per hour. And we chose this route because it really have recurrent congestion during morning peak hours, and all the traffic patterns are present in this route. And so we only have 1.5 months of traffic data used for the neural network training, but the system evaluation used 8.5 months. So it's very unusual in comparison to most published systems. They usually use larger data for training and smaller data for testing. So the testing data consists of over 3.8 million data points. And we predict the future speed from T0 is the starting point up to 30 minutes. You can go on if we would like to. And you can see the performance here. And this is the performance of speed prediction, the error. As we go on, you can see at 5 minutes error, about 2 miles per hour error margin. As we predict more in the future, and of course the error increases at 30 minutes, the average error is about 6 miles per hour. And also we improve, this shows the improvement our system at each time interval over the baseline. Baseline is we taking the speed recorded at a t equal to 0. If you just use that speed as your predictive speed profile, then the error will be much larger than what our system can produce. So this just shows the improvement. And this just shows the system performance comparison with some of the published work, as you can see. And a lot of them are really having very small test data. This is only 6 days, and their mean average error is 9%. And this one, we have the prediction about 30% of 2 days data. And prediction interval 5 minutes and 10 minutes. And this one have 4-day data. Prediction is 15 minutes in the future. And this use 1-day data. However, their system predicted 2 minutes, 4 minutes, all the way to 60 minutes. But it's only really 1-day data. We use 260-day data, 52 sensor data along the road. And our prediction error, you can see much better than those published results. So this is when, once we have the spot speed predicted, then we can use the dynamic traverse algorithm to piece together the speed profile from any origin to the destination. And so this just shows you the difference. If currently we use 2 categories, Monday through Friday and a weekend. Then also people will say, why you are using 2 categories? So this system uses all weekday, only one type of system. And you can see the benchmark is the choose, and this is the green one is our current system. Blue one is that if you don't care weekend or weekday, the performance is the blue curve. Obviously, it's not as good as the green one. And this is another performance example. This baseline is the green one, which means it just take the sensor data at a t equal to 0. And our benchmark, the red one is the choose of the sensor at the time when the car traveled to that spot. And our blue one is our system. You can see it's very close to the red one as, in this case. But anyway, so I don't know. I have 2 more, research examples, but I think I may run out of 3 minutes. That's wonderful. Okay, the next project I will introduce is that the previous one, I will predict the traffic sensor data on the freeway, from A to B. But for the auto company, they want to also learn individual driving data. So you and I will drive very differently on the same route, same time, right? Personal driving. Some are more aggressive, some are more cautious. So how are we going to really predict the personal driving data? And this, so the personal driving data, it's very challenging, everyone's different, but if we mathematically, we analyze it, every driving will be always consist of a local, then 2 ramp, then the freeway, ramp, freeway, and so forth. In this example is that starting at Novi, Michigan, ending at Dearborn, only 26 miles, so 2 local routes, and 3 freeway sections. You can see 3 different freeway sections, and also 4 different ramps. So those are the complexity we have to do, because same driver on these different roads or have complete different speed profiles. So we need to learn. And so we developed a system to train to predict the speed on the local route for every individual driver. I'm going to go very fast. And it just, in the local, it's the most complicated one, and also can see most of the driver's pattern, actually. And this is considered free flow area. And you can see at the traffic light area, complete different pattern than this one. And then you go back to free flow, and the stop signs are also different. And different driver could be different. Some stops, people even hard to stop. This traffic light again, and the free flow again. So it's very complicated in the free local area. So we develop a different neural network system for those different scenarios. But more complicated is that because eventually the system will be loaded into a vehicle. So a vehicle can have different drivers, right? Wife, husband, kids, and so forth, friends drive. So really the driving profile speed can be categorized in the following. One is the same driver, same route. So we somehow can detect if the driver is A, B, C, D, and there are ways to do it. So the same driver can drive the same route every day, like you drive to work every day, right? Pretty much take the same route, except some, you have to take get something done. The next category will be different driver, but you drive the same route, okay? Someone else is driving the car, but the route is about the same. Then I can predict the speed as well, your driving speed. And this will be the same driver, of course. Eventually, a driver can take a different route. So how do I predict the speed on the different route? And this is the most difficult part is this one, different driver and different route. I have to predict it. And I'll show you the performance. So as you can see, for the same driver, same route, and we have improvements over the baseline, which is the sensor give the speed profile. And you can see the same driver, same route, we can make a prediction improvement 43%, which is very high. And same driver, different route, about 30%. Different driver, same route, about 36% improvement. And the most difficult part is the different driver, different route, what we have, okay? Do I have time? Okay, this one is that we use the deep learning net for the lane change prediction. And lane change probably causes a lot of traffic accident. And you make the lane change, you didn't see other cars coming and so forth. So the lane change thing is, what do we mean by prediction? Prediction is different than detection. Prediction is that we try to think, we think the driver or the system think the driver is going to make a change. And so what we do is that, I only have 1 minute. Instead, a lot of people will use the vehicle signal to detect the lane change. It's different than what we do. We are trying to predict the driver going to make a lane change before the driver actually moving the wheel. So how can we do that? So we use the driver's physiological signals. So a person trying to take action that reflect in your brain. And also we think there will be pattern in your physiological signals such as heart rate, respiration, and skin conductance. Those are the major signals we use. So the device provided with us 32 signals. Some of them could be more important than the other. So immediately we know in the computer vision or pattern recognition, you will decide what signals are more important than the other, what are the features. It's very complicated. So that's why we use the deep learning convolutional neural network. Now it is different from the image because those multiple signals, you can stack them together and they have temporal domain features, but they really don't have much spatial domain, not like in the image, right? You have the 2 dimensions. So that's why we have used the one-dimensional convolutional filter to apply to each signal and try to detect the features we need for the lane detection change. But I think I overrun the time. So I will stop here and take questions.
Thank you so much for the speech. So actually, I have 2 questions, but the second one you already kind of answered because in the last couple of slides. The first one, all the big data you're collecting has to do with the perfect day scenario of you're detecting the traffic in Ohio and Michigan. Let's say just you implemented the sensors and everything. But how about when they have some events, let's say a football match? I mean, everybody drives in not in the normal way that they do. One more thing, you covered in the last 2 slides, you said that you can measure the emotional tendencies for the drivers. So my question is, where did you implement that in your equation, and how accurate those 32 factors that you just said you can cover, and how fast you can predict the response? I mean, let's say everybody can just have a different day if they having some circumstances in their families, they didn't wake up on time, or they can change in a minute. How accurate you can predict those emotions of those drivers to be able to be proactive for some actions?
Right, and very good question. I just want to let you know, all the data we use are all real-world driving data. It's not simulated data. So actually things do happen in those data. Especially we talk about V2V communication, we have over 3,000 vehicles running over 2 years. It's a lot of data to crunching. So a lot of patterns are contained in that. So you actually raised two different questions. For example, you said people driving, every day, they can change route. How can I predict? I can't. The learning part will depend on historical data. And as new data coming, I will try to learn, but will give me some data and time to learn what route you are taking. So that part actually very important is that you to do the incremental learning, because each car should have a different system. You should learn the driver, individual will be different. So that's a very good question. It is a learning process. That's why we're building the system. It's all data-driven, okay? Actually, then you talk about the driver's emotion and lane change, right? It is very difficult. We try to predict the lane change 2 seconds before it actually crossing the lane. That's what the auto company want to do. And actually, I have some results, but we can predict probably in the regular neural network about 70% of the time, but with the deep learning, we can really improve quite a bit in the 80% range. But still, the data is very difficult to collect because the V2V, there are 3,000 vehicles. Those data don't have the physiological signals. So we recently received a big research contract from Toyota Research Institute, and they are asking us to build 4 different data set equipment. We'll collect the elder drivers' data because those kind of things change, cause danger mostly for senior drivers. So that's what they want to do. But they want to collect a whole lot more data. And very good question. Thank you. Okay. Thank you very much.
And finally, before the coffee break, please, Mr. President Mashhour, Dr. Professor Mashhour, and Professor Arafat, allow us to reward our keynote speaker and supporter. Professor Yi Murphey, University of Michigan-Dearborn, USA. Professor Omar Rana, Cardiff University, London. Dr. John Omen, Carleton University, Norway. Professor Christian Potey, University Grenoble, France. And Professor Adnan Shaoud, University of Michigan-Dearborn, USA. Professor Osama Rawajde, Auckland University. Professor Giorgio Cuscito, University of Cagliari, Italy. Professor George Dafalos, Middlesex University. He's not here? Okay, he's not here. Professor Vahoof Cohen, University of Hasselt. And finally, allow us to thank the Scientific Research Support Fund, Ministry of Higher Education and Scientific Research in Jordan, ممثلة بالسيد Mr. مجيب شبول. Thank you very much.